96% of their bullets were hitting nothing but air. Not occasionally, not as a failure mode, consistently, systematically. Every single day over Europe and the Pacific, thousands of American gunners were firing hundreds of thousands of rounds at enemy aircraft and missing almost all of them. The mathematics were so brutal that military analysts initially thought their data was wrong. They rechecked it, reviewed gun camera footage again, ran the numbers a third time. The results didn't change. By 1943, trained American aerial gunners, men, who had completed rigorous training, who had practiced extensively, who had every motivation to hit their targets, were achieving hit rates below 4% against crossing targets. In a typical 10-second engagement where a Browning M2 could fire roughly 130 rounds, perhaps 5 bullets would actually strike the enemy aircraft. 5 hits from 130 rounds. That's not marksmanship failure. That's not a lack of courage or commitment. That's physics declaring that human intuition is completely wrong when dealing with objects moving at 300+ miles per hour. The problem had a name: deflection error. And it was about to kill tens of thousands of people before anyone figured out how to solve it. But here's the thing that nobody expected. The solution wouldn't come from better equipment. It wouldn't come from longer training. It would come from understanding that human brains are fundamentally incompatible with the speeds of aerial combat, and that the only way to win was to train people to do something that felt completely wrong. The story of deflection shooting is the story of a military crisis that nobody saw coming, a physics problem that nobody knew how to solve, and a solution so counterintuitive that it took actual combat losses before people would believe it worked. It's the story of how you train someone to aim at empty sky and trust that their bullets will hit metal, and it changed everything, from World War II fighters to the F-22 Raptor to the missile systems protecting aircraft carriers right now. The problem started with an assumption that seemed perfectly reasonable. When you want to hit something with a bullet, you aim at it. You point your weapon at the object you want to strike. You pull the trigger. The projectile travels from the barrel to the target and impacts. This is how rifles work on shooting ranges. This is how hunters shoot deer. This is how every human has ever thought about hitting something with a projectile. Aim at the target. The target gets hit. But aerial combat operates under different rules. Rules that human intuition never evolved to handle. Rules that didn't exist for 99.9% of human history. In 1943, when American bomber gunners were encountering these rules, they were encountering something their training hadn't prepared them for because their training couldn't prepare them for it. The physics were too counterintuitive. The speeds were too extreme. The available time was too short. A Zero fighter approaching at 300 miles per hour covers 440 feet every single second. At a typical combat range of 300 yards, 900 feet e. 50 caliber Browning M2 bullet needs approximately 0.31 seconds to travel that distance. The muzzle velocity is roughly 2,900 feet per second, which sounds fast until you do the math and realize that 0.31 seconds is an eternity in aerial combat. In those 0.31 seconds while the bullet is in flight, the enemy aircraft moves another 136 feet. That's 11 car lengths. That's nearly the entire length of a football field. The gunner aims where the aircraft is. The bullet arrives where the aircraft was a third of a second ago. Empty air. The enemy fighter continues untouched. This happened over and over and over again. Gun camera footage from 1943 missions shows the pattern repeatedly. Initial bursts with some forward lead, followed by progressive bursts walking backward. As the gunner visually corrected what he thought was leading too much, he was self-correcting in exactly the wrong direction, trusting his eyes over the physics he couldn't see. If you're realizing that this is a story about how human intuition can betray us at the worst possible moment, and how one counterintuitive technique could double kill rates in just 8 weeks, hit that subscribe button because what comes next is going to blow your mind. Drop a comment on whether you would have figured out that aiming at empty sky is the solution. And keep watching because the answer involves some brilliant physics and some equally brilliant psychology. The statistics were apocalyptic. In 1943, alone, the 8th Air Force flying bombing missions over Europe lost approximately 1,400 bombers. That's roughly 116 per month. Each B-17 carried a crew of 10 men. That meant approximately 1,860 air crewmen were being killed, captured, or going missing every month. Many of those deaths occurred specifically because the bomber formations couldn't effectively defend themselves against fighter attacks. They had guns, they had ammunition, they had trained gunners, but they couldn't hit anything. The psychological impact on crews was catastrophic. You're flying in formation at 25,000 feet, oxygen mask fogging, temperature 50 degrees below zero, knowing that German fighters are coming. Your only defense is the gunners in your aircraft. Then you watch those gunners fire thousands of rounds while enemy fighters penetrate the formation untouched. You watch bombers explode around you. You realize that the defensive fire you're relying on for survival is completely ineffective. The October 1943 missions to Schweinfurt and Regensburg were particularly brutal. 60 bombers failed to return out of 291 dispatched, a 20% loss rate. Survivors landed with dead and wounded crewmen, shredded hydraulic systems, engines trailing smoke. The crews reported the same frustration in debriefings. The guns were working, the ammunition was flowing, but the bullets weren't connecting. By 1943, it was clear that something fundamental was wrong with how America was training its aerial gunners. The Army Air Forces had established the Flexible Gunnery School at Laredo, Texas in 1942. They put students through rigorous programs. Trainees spent hours in turret simulators. They studied diagrams showing proper lead angles. They shot at towed targets being dragged behind trucks. Some received as little as 4 weeks of training before being deployed to combat. By late 1944, that had expanded to 8 to 10 weeks of training with 5,000 practice rounds instead of 1,000. But the fundamental problem remained. You could teach the mathematics of deflection in a classroom. You could show students the diagrams. You could even have them practice shooting at moving targets on the ground. But when they got into actual combat, under stress, facing enemy aircraft that were trying to kill them, most of them reverted to instinct. They aimed at the visible target. They watched their bullets miss, and they lived long enough to repeat the mistake again. The technical problem was clear: deflection error. Against a target crossing at 90 degrees at 300 yards distance, a gunner needed to aim approximately 15 to 20 feet ahead of the aircraft's nose. That meant putting your crosshairs on what looked like empty sky. Completely empty. No visible target. No obvious point of aim. Just empty space that hopefully contained the future trajectory of an enemy fighter. Every human instinct screamed that this was wrong. Every natural instinct suggested that leading that far ahead would result in an even worse miss. The brain said, reduce the lead. Get the target visible in your sights. Trust what you can see. The physics said, stop trusting what you can see. The target won't be there. Lead farther. Trust the mathematics. The problem was that human brains evolved to throw spears at animals moving at 20 meters, not to aim at fighters moving at 300 mph. The cognitive systems that had kept humans alive for 200,000 years were fundamentally incompatible with the speeds of modern warfare. If this realization about the gap between human intuition and physical reality is starting to grab you, the idea that our brains can be catastrophically wrong about high-speed problems, hit that like button and keep watching. Drop a comment on whether you think the solution would come from better training or better equipment. And keep watching, because MIT was about to create something that proved there was a third option nobody had thought of. The solution had been sitting in a filing cabinet since 1924, not forgotten, not buried, just waiting. 20 years before. The crisis became obvious. Military theorists had recognized that as aircraft speeds increased, the deflection angles required to hit them would become so large that conscious calculation alone couldn't handle it. The solution wasn't to train human brains faster. The solution was to build a machine that could do the calculation. The flexible gunnery school at Laredo had been trying to solve the problem through training, extended programs, more practice rounds, more realistic target scenarios. By late 1944, they'd created a particularly effective method, motorized turrets firing at targets being towed by high-speed boats at 50 to 60 km, while the distance and crossing angles varied randomly. Gunner trainees engaged these targets repeatedly, 50 to 70 passes per training day, until the act of leading became automatic. It was training that bypassed conscious thought entirely, embedding deflection correction at the same neurological level as walking or catching a thrown ball. This required thousands of practice rounds and weeks of intensive training, but for the gunners who got it, muscle memory took over. Under stress, their hands maintained proper deflection automatically even when their conscious minds were terrified. But there was a parallel track running at MIT. Charles Stark Draper's team at the Radiation Laboratory Division 7 was building something different. Not a training solution, a mechanical solution. They were creating a machine that could solve the deflection equation in real time. The Mark 14 Gyro Computing Gun Sight was a mechanical computer. Inside the sight housing were gyroscopes, spinning spheres maintaining precise orientation through pure physics. Cams, carefully shaped pieces of metal that converted input into output angles, and mechanical linkages that continuously updated the firing solution as variables changed. The gunner would track a target normally, moving the turret to keep the enemy aircraft in view. The sight's gyroscopes would continuously measure the rate of turret movement. The cams would convert that rate information into real-time deflection corrections. The result: the sight's reticle would automatically position itself at the precise lead angle required to intercept the target. The gunner didn't have to calculate anything. He didn't have to estimate. He aimed the sight's reticle directly at where he saw the target, and the mechanical computer behind the reticle positioned his bullets where the target would be. Navy testing at Norfolk in 1943 to 44 showed the results. Gun camera footage before the Mark 14 showed hit rates hovering around 5%. With the computing sight installed, hit rates jumped to 15 to 25% within the first few weeks of implementation. A 3 to 5-fold improvement in effectiveness. That meant fewer bombers shot down. That meant fewer crews dying. That meant the bombing campaign would actually achieve its objectives instead of collapsing under casualties if this story about a mechanical computer doing something the human brain couldn't do is starting to show you the fundamental difference between training and equipment, and how sometimes you need both. Hit that subscribe button right now because the implications extend far beyond World War II. Drop a comment on whether you think equipment or training mattered more for solving the deflection problem. And keep watching because the real revolution came when they combined both approaches. The transformation from 4% hit rates in early 1943 to 20% plus by late 1944 wasn't caused by any single solution. It was caused by a combination of 3 separate innovations converging at exactly the right moment. First, there was the understanding of the physics. The mathematics of deflection had existed since the 1920s, but military doctrine hadn't incorporated it into training. By 1943, that understanding was finally being translated into training methodology. Second, there was the equipment solution. The Mark 14 computing gun sight was revolutionary because it removed the conscious calculation requirement. Gunners who used it didn't have to understand the math. They just had to use the sight. Third, there was the training evolution. The Flexible Gunnery School and the Naval Air Gunner School at Jacksonville had figured out how to embed deflection correction into unconscious competence through repeated practice at realistic speeds with immediate feedback. Each approach had advantages and limitations. The Mark 14 was perfect for scenarios where you could track targets systematically. But production limitations meant only a fraction of aircraft could be equipped. Training was universal. Every gunner could benefit, but it required time and ammunition that didn't always exist. The combination produced results that neither could achieve alone. By 1944, elite gunners who had survived 30-plus missions demonstrated something remarkable in combat footage analysis. Their deflection aim points remained stable even under extreme stress. When a FW-190 came screaming through the formation with cannon fire flashing from its wings, these experienced gunners maintained their lead automatically. Their conscious minds could be absolutely terrified. Many admitted to being convinced they were about to die. But their hands kept the proper sight picture anyway. They'd achieved what martial artists call mushin, the state where technique happens without conscious direction, where the body knows what to do because the body has done it 10,000 times before. But that level of proficiency took time and ammunition most gunners never received. The mathematics of wartime were brutal. If creating an expert deflection shooter required 5,000 practice rounds and 10 weeks of intensive training, but the bomber offensive needed 50,000 new gunners in 6 months, compromises were inevitable. Most gunners flying combat missions never achieved true unconscious competence. They remained in the conscious competent stage, capable of proper deflection when conditions allowed them time to think, but vulnerable to collapse under stress or when facing unexpected situations. This created a strange stratification in combat effectiveness. A bomber formation's defensive capability wasn't uniform. It depended entirely on which specific gunners were in which specific positions. A formation that happened to include several veterans with deep training could fight off attacks that would devastate a formation of newer crews. German fighter pilots learned this quickly. They targeted bombers that showed hesitant or inaccurate fire during initial passes. They avoided formations where the defensive fire was immediate, heavy, and precisely placed. If you're realizing that this is a story about how training and equipment need to combine, and how human skill matters even when machines are helping, hit that like button and subscribe, because the lessons extend far beyond World War II. Drop a comment on whether you think modern pilots still need to practice deflection shooting. And keep watching, because the answer might surprise you. The Mark 14 computing gun sight became the foundation for every deflection solution that came after. After the war, it evolved into the Mark 18, which served through the Korean War. Then digital fire control computers emerged, capable of processing dozens of variables simultaneously. By Vietnam, fighter aircraft carried radar-assisted gun systems that calculated deflection automatically. Pilots only had to keep targets within acquisition parameters. The F-4 Phantom's lead computing optical sight did in fractions of a second what had taken Draper's mechanical gyroscopes significant time. Modern air-to-air combat has largely moved beyond guns entirely. Missiles handle interception at ranges where deflection would require leading by miles. But the underlying principle hasn't changed. An AIM-120 AMRAAM missile uses inertial guidance and active radar to continuously update its trajectory toward where its target will be. It executes deflection calculations thousands of times per second. The F-22 Raptor's AN/APG-77 radar doesn't just track targets. It predicts future positions based on current velocity and acceleration. It positions the aircraft and selects weapons accordingly. Same problem that WT gunners struggled with. Same solution. Calculate where the target will be instead of where it is. Just implemented with computers processing terabits per second instead of gunners manually estimating angles. What's remarkable is that deflection shooting fundamentals remain part of modern fighter pilot training. Despite guns being tertiary weapons in contemporary air combat, the Navy Fighter Weapons School, Top Gun, still teaches basic fighter maneuvers that include guns-only engagements. Not because pilots expect to dogfight with cannons. Modern combat happens at beyond visual range where missiles dominate. But deflection shooting training develops spatial awareness that applies to every aspect of air combat. A pilot who's mastered leading a maneuvering target intuitively understands closure rates, angle off, and lead pursuit curves. Concepts that matter whether firing a cannon or positioning for a missile shot. The training carries forward. The lessons extend beyond aviation into every domain involving fast-moving targets. Modern anti-aircraft systems like the Phalanx CIWS protecting naval vessels are essentially sophisticated implementations of what WWII's gunners struggled to do manually. The Phalanx fires 4,500 rounds per minute, 75 rounds per second, at incoming missiles and aircraft. Its radar continuously calculates deflection and updates aim point. It makes the same corrections bomber gunners needed in 1943, just faster and without the human hesitation that cost so many lives. Even video games that simulate combat incorporate deflection mechanics, teaching the same counterintuitive principle. War Thunder and Digital Combat Simulator require players to lead moving targets manually. New players experience the exact same frustration WWII gunners felt, watching their tracers arc harmlessly behind enemy aircraft until they internalize that leading is necessary. The most skilled players develop the same unconscious competence that combat veterans achieved. Their hands adjust aim without conscious thought. They've internalized the principle through thousands of repetitions with immediate feedback. If this evolution from wet deflection, shooting to modern F-22 systems to video game, training is showing you how one solved problem becomes the foundation for centuries of innovation. Hit that subscribe button right now and turn on notifications. Drop a comment on whether you think WWII soldiers would be amazed or unsurprised by modern automated deflection systems. And keep watching because the final piece of this story is about what the deflection shooting problem teaches us about human adaptability. The transformation from 4% to 20% plus hit rates represents one of the most dramatic tactical improvements of World War II. Thousands of air crewmen who would have died continued flying. Enemy fighters that would have escaped went down in flames. Bombing campaigns that might have failed reached their targets. All because someone finally acknowledged that human instinct, however strong, could be catastrophically wrong. The gunners who learned to aim at empty sky, who forced themselves to fire at nothing visible and trusted their bullets would meet metal, they proved something essential about human adaptability under pressure. We're not prisoners of our instincts. With proper understanding, sufficient training, and enough desperation, we can rewire our responses to match reality rather than demanding reality match our intuitions. The problem was physics. The solution required understanding that problem so completely that you could reprogram human behavior to work with it instead of against it. That lesson, born in blood over Europe and the Pacific, remains relevant wherever humans confront situations where instinct and solution point in opposite directions. If this entire story about how a physics problem that killed thousands was finally solved through training and mechanical innovation, and how that solution became the foundation for everything from Korean warfighters to F-22 Raptors to modern air defense systems, has gripped you, hit that like button and subscribe right now. Drop a comment on what physics problem you think we're currently getting wrong in modern warfare. Share this video because the lessons about the gap between human intuition and physical reality apply everywhere. And thank you for watching how one counterintuitive technique double-checked the kill rate of an entire generation of combat crews and changed military technology forever. The question isn't whether Curtis Culin was a hero. That's the wrong question entirely. Heroes are people who act despite fear, despite uncertainty, despite knowing the probable outcome. Curtis wasn't acting despite anything. He was acting because of mechanics, because of logic, because he saw a problem and his mind automatically began calculating how to solve it. That's not heroic. That's just how his brain worked, but the innovation itself, the Hedgerow cutter, that was something else entirely. It was a moment where practical thinking met urgent need, where one person's refusal to accept an unsolvable problem created a cascade of consequences that rippled through an entire military campaign. The real story isn't about Curtis being special. It's about what his invention reveals about how organizations handle ideas. The Normandy breakout in July 1944 happened because General Omar Bradley and his staff were willing to listen to a sergeant. That's the actual revolutionary moment, not the welding, not the design, not the testing. The revolutionary moment was when a mechanic from New Jersey was allowed to propose something that sounded insane. Take a damaged tank, weld scrap metal to it, drive it at a wall at full speed, and military leaders said, "Yes, let's try that." How many organizations would do that? How many would listen to someone at Curtis's level in the hierarchy? How many would value the practical insight of a mechanic over the theoretical knowledge of engineers? How many would allow a test with high stakes and uncertain outcome? In the modern world, we talk constantly about innovation. Innovation is the most valuable commodity. Innovation is what separates winning companies from failing companies. Innovation is what drives progress. We say we want innovation. We say we value creative thinking. We say we empower people to suggest new ideas, but do we actually do it? Or do we just say we do it while protecting our hierarchies and defending our existing solutions? The answer is usually the latter. Organizations create systems that prevent innovation. Risk-averse cultures that punish failure. Hierarchies that ensure that ideas flow top-down instead of percolating from the ground up. Formal processes that strangle creative, thinking under layers of procedure and protocol. Curtis Culin would never be allowed to propose his hedgerow cutter solution in most modern organizations, an undereducated sergeant suggesting a solution that experts had overlooked. That's not how organizational culture works. He'd be politely thanked, his suggestion would be filed away, and the official engineers would continue, working on official solutions through official channels. And the hedgerow problem, the actual problem that was bleeding the invasion dry, would continue to get worse. That's the real lesson of Curtis Culin. Not that one man changed history with a good idea, but that organizations capable of listening to people at every level are capable of solving problems that organizations stuck in rigid hierarchies cannot. In 1984, when David Carter interviewed Curtis, the historian asked him directly, "What do you think would have happened if General Omar Bradley had dismissed your idea?" Curtis had thought about this question many times over the years. Decades of reflection had led him to certain conclusions. "The hedgerow problem would have gotten worse," Curtis said quietly. "Not better. The engineers would have kept trying complex solutions. The generals would have kept assuming that brute force would eventually work. The casualty rates would have climbed, and sooner or later, the invasion would have stalled so badly that it threatened the entire strategic outcome of the war." How much worse? Carter pressed. "I don't know," Curtis admitted. "But I know that the problem was as fundamental as problems get. You had thousands of tons of military hardware trying to accomplish a tactical objective and failing repeatedly. Something had to change. Either someone would eventually think of a simple solution, or the problem would lead to crisis-level casualties. In your opinion, was it inevitable?" Carter asked. "Would someone else have eventually thought of the hedgerow cutter if you hadn't?" Curtis considered this for a long time. "Probably," he finally said. "Someone eventually would have realized that cutting through was better than climbing over. Someone would have thought about using captured obstacles as cutting implements. But the timing mattered. The solution needed to come when it did, early enough in the campaign that it could be deployed at scale. If it had come a month later, it wouldn't have mattered as much. If it had come earlier, it would have mattered even more. The timing was crucial." "So you were lucky," Carter said. "Impossibly lucky," Curtis agreed. "Lucky that I saw the problem. Lucky that Captain Morrison was willing to let me try. Lucky that the first test worked. Lucky that the higher command approved production. Lucky that the supply chain could handle manufacturing thousands of units. Any one of those things could have gone differently, and the entire outcome changes." But there's another question embedded in Curtis's story, a harder question that nobody wanted to ask. How many soldiers died because of the Hedgerow cutter? Not the soldiers it saved. The soldiers it killed, German soldiers. Young men, same age as the American soldiers fighting a war they hadn't started. Soldiers positioned behind hedgerows, expecting to hold defensive positions. Suddenly vulnerable when American tanks burst through barriers that were supposed to be impenetrable. Curtis never calculated an exact number. He knew it was significant. Thousands, probably. Tens of thousands, possibly. But he never tried to quantify it precisely because doing so would require confronting a moral question that didn't have a clean answer. The Hedgerow cutter was simultaneously a life-saving innovation and a death-dealing weapon. Both things were. True, soldiers lived because of it. Soldiers died because of it. You couldn't separate those two outcomes. They were inseparable. The same invention that made tanks effective at breaking through hedgerows made tanks effective at killing German soldiers who were defending those hedgerows. Was this morally justified? Curtis would eventually come to believe it was. German had started the war. German aggression had necessitated this response. The soldiers defending Normandy were fighting for a regime that had committed atrocities. The invasion itself was morally justified. Therefore, the innovations that made the invasion more effective were morally justified, but that intellectual framework didn't prevent Curtis from having nightmares for the rest of his life. It didn't prevent him from thinking about German families who didn't know their sons had died. It didn't prevent him from understanding that on the other side of the war, there were people grieving just as deeply as Americans grieved their losses. The moral weight of innovation is never simple. There's a photograph from October 1944 that shows Curtis receiving a commendation from General Omar Bradley. They're standing in a field somewhere in France. Curtis is uncomfortable in his formal uniform. Bradley is composed, professional, a general distributing recognition to a soldier who has earned it. But if you look closely at Curtis's face in that photograph, you can see something in his eyes. Not pride, not satisfaction, something more like resignation. He knows what he's being recognized for. He knows that the commendation represents not just an innovation, but thousands of deaths. Bradley knew it too. That's why the recognition felt necessary, to acknowledge Curtis's contribution, to validate the choice to listen to a sergeant when everyone else said the problem was unsolvable. But Curtis never got comfortable with the recognition. Over the following decades, he gave a handful of interviews. Military historians who tracked him down. Documentarians making films about WWII innovations. Television programs looking for authentic veteran perspectives. Each time, Curtis answered the questions honestly but without enthusiasm. He seemed to accept interviews as an obligation, not because he enjoyed revisiting these memories. The consistent theme in every interview was the same. I was just a mechanic. I solved a problem. That's all, but that's not all, of course. Because the Hedgerow cutter wasn't just about military innovation. It was about organizational culture, about whether hierarchies could listen to ideas from unexpected sources, about whether good ideas could compete based on merit rather than the source of the idea. And in those dimensions, Curtis Culin's story became increasingly relevant as the decades passed. By the 1990s, American business culture was beginning to recognize that innovation couldn't be controlled from the top down. Companies like 3M implemented policies encouraging employees to spend time on projects outside their assigned responsibilities. Google would eventually formalize this into their famous 20% time policy. Silicon Valley culture began to celebrate disruptive ideas and reward people who challenged conventional wisdom. These weren't new ideas, but they were becoming mainstream business practice, and Curtis Culin's story kept getting cited as a historical precedent. Look at what happens when you listen to people at every level, the arguments went. Look at Curtis the mechanic who solved a problem that generals and engineers missed. Look at how willingness to try unconventional solutions led to breakthrough innovation. Look at how ignoring hierarchical authority in favor of merit-based evaluation of ideas changes organizations. Curtis didn't know any of this was happening. He was retired. He was living in New Jersey. He was fixing cars for close friends and family, but mostly he was trying to live a quiet life away from recognition and attention. When he died in 1993, he probably didn't realize that his wartime invention was becoming a case study in business schools. He probably didn't realize that his story would eventually be used to argue for organizational change. He probably didn't realize that by 2000, 2010, 2020, decades after his death, his example would still be cited when people argued that the best ideas come from solving real problems, regardless of who identifies them. The Normandy campaign lasted from June 6, 1944 to August 30, 1944. During that period, approximately 5,000 Sherman tanks were equipped with Hedgerow cutters. Those tanks were responsible, directly and indirectly, for breaking German defensive lines, enabling the Allied breakthrough, and setting the stage for the rapid liberation of France. Military analysts estimate that the campaign was shortened by weeks because of the Hedgerow cutter. Every week of campaign shortened meant fewer soldiers killed in combat, fewer civilian casualties from prolonged fighting, fewer resources consumed in extended warfare, accelerated liberation of occupied territories, faster approach toward German defeat. The mathematics are staggering. One sergeant's welding work cascading through an entire military campaign, through an entire continental military strategy, through the entire trajectory of World War II in Europe, but numbers don't capture the actual impact. The actual impact is Sergeant Patterson, the tank driver who carried Curtis's first prototype through that Hedgerow, surviving the entire war and returning home to Tennessee where he became a schoolteacher. The actual impact is Private Kowalski living through the entire Normandy campaign, surviving further combat, and eventually moving to Chicago where he worked as a union organizer for 40 years. The actual impact is thousands of individual lives that were preserved. The actual impact is the families of those soldiers, children born who otherwise wouldn't have been born, grandchildren and great-grandchildren, an entire cascade of human existence that flows from the fact that Curtis Culin decided to solve a mechanical problem. When Curtis said, "My invention mattered, Curtis," don't ever doubt that, he was speaking literal truth. Not metaphorical, literal. The existence of millions of people is tied to whether Curtis successfully welded those prongs to that first tank. That's the real weight of innovation, not abstract impact on military campaigns, not recognition by generals, not citations in history books. The real weight is knowing that your actions ripple through time in ways you can never fully calculate. If you're beginning to understand why Curtis Culin's story matters beyond military history, if you're thinking about how your own actions might ripple through time in ways you don't realize, hit that subscribe button right now because the themes in this story apply to your life. Drop a comment on whether you think Curtis deserved more recognition or whether he was right to stay humble about his achievement. And keep watching because the final section reveals why this story matters to us right now, in 2024, when we desperately need innovation, but our organizations keep strangling it. There's a philosophical question embedded in Curtis's story. The question is, does innovation require genius or does it require permission? The traditional narrative says that innovation requires genius, the brilliant individual who sees solutions nobody else can see, the rare talent who understands problems on a deeper level, the genius who changes the world through intellectual brilliance. Curtis Culin wasn't a genius. He was smart, certainly. He understood mechanical systems. He could calculate angles and forces. He could execute complex welding work. But he wasn't extraordinarily intelligent. He was a mechanic, a practical, competent, intelligent mechanic, but he was allowed to try. That's the real innovation, not the welding, not the design. Permission. Curtis was given permission to do something unconventional with untested equipment in a high-stakes environment. That permission was rare. That permission was valuable. That permission changed everything. Imagine if Captain Morrison had said no. Imagine if he'd responded to Curtis's proposal with, "That's an interesting idea, Sergeant, but we need to go through proper channels. File a report with battalion. We'll forward it to divisional engineering. Let's see what the experts say." By the time the idea filtered through official channels, it would have been buried under skepticism and competing priorities, but Morrison didn't say that. Morrison said yes, and that yes, that permission to try cascaded into a changed military campaign and a changed historical outcome. How many other ideas are being killed right now because the wrong person said no at the wrong moment? How many Curtises are out there, seeing problems that could be solved, but not being given permission to try? In 2024, the problem isn't that we lack innovation. The problem is that we lack permission for innovation. We create innovation labs and hire innovation consultants and read books about disruption and agile methodology. We say we want creative thinking. We say we want people to challenge the status quo. We say we want breakthrough solutions. But then we structure organizations that prevent those things. We create hierarchies that ensure ideas flow top-down. We create processes that strangle unconventional thinking. We create cultures where failure is punished rather than learned from. We create systems where being wrong is worse than being boring, but conventional. And then we wonder why we don't have Curtis Culin. We don't have Curtis Culin because we don't give people permission to be Curtis Culin. We don't have permission cultures. We have compliance cultures. We have process-driven cultures. We have risk mitigation cultures. We have cultures that have optimized for consistency at the expense of breakthrough. Curtis's innovation required 4 elements. Recognition of a real problem, Hedgerow stalemate. 2. Willingness to try unconventional solutions, Weld scrap metal to tanks. 3. Permission to test despite potential failure, Captain Morrison said yes. 4. Rapid iteration and scaling. If initial tests worked, 5,000 units manufactured. Most modern organizations have element 1. They recognize problems. Most modern organizations completely lack elements 2 through 4. We don't allow unconventional thinking. We don't give permission to test unconventional ideas. We don't iterate rapidly. We don't scale aggressively when initial tests work. We optimize for process instead of outcome, and the cost of that optimization is innovation. The cost is the thousands of Curtis Culins working in modern organizations who will never propose their hedgerow cutters, because the organizational culture has already told them that unconventional ideas from unexpected sources won't be taken seriously. Curtis Culin died in 1993 for the remaining 30 years of his life after World War II. He was mostly anonymous. He fixed cars. He raised a family. He lived quietly in New Jersey. He was remembered by his family, by his friends, by the occasional military historian who tracked him down. But he wasn't remembered by the wider world. Most people have no idea who Curtis Culin was. They've never heard the story. They've never learned how one mechanic's welding work changed the course of World War II. They've never considered what it might mean for their own organizations and their own approach to innovation, but his legacy persists. In military museums, the hedgerow cutters are preserved. Chunks of steel welded to Sherman tanks, physical evidence of innovation. Plaques explain what they are and what they did. Occasionally they mention Curtis Culin, the mad mechanic who refused to accept that problems were unsolvable. In business schools, his story is cited when professors teach about organizational culture and innovation. In history books about World War II, the hedgerow cutter is recognized as one of the most significant tactical innovations of the war. But most importantly, Curtis's legacy exists in the minds of people who understand a crucial lesson. Breakthrough innovation often doesn't come from the places we expect it to come from. It comes from a sergeant with a notebook. It comes from a mechanic looking at a problem from a different angle. It comes from someone who wasn't supposed to solve the problem but did anyway. It comes from permission. The hedgerow cutters saved thousands of lives. They shortened a campaign that would otherwise have ground on, consuming resources and soldiers at catastrophic rates. They proved that seemingly insurmountable tactical problems could be solved through practical thinking and willingness to try unconventional approaches. They changed tank warfare doctrine. They accelerated the liberation of France and Europe. All of that is true. But the deeper legacy of Curtis Culin, the legacy that matters even more than the tactical impact, is this. The best ideas don't always come from the place you expect them to come from. Permission matters more than credentials. Listening to people at every level of your organization matters more than protecting the authority of experts. Willingness to try something unconventional matters more than consistency. Rapid iteration matters more than perfect. Planning. Curtis was just a mechanic. But he was a mechanic who was given permission to solve a problem. And he did. That's the story that matters. Not the medal. Not the commendation. Not the historical recognition. The permission. If you understand now why Curtis Culin deserves to be remembered, not as a war hero, but as a lesson about organizational culture and innovation, hit that subscribe button right now because this is the lesson that applies to your own life, your own work, your own organizations. Drop a comment on what unconventional solution you've been afraid to propose because your organization has shown you that unconventional ideas aren't welcomed. And share this video because Curtis's story needs to be heard by people in positions of power, by people who can say yes to unconventional ideas, by people who can create permission for innovation to happen. Curtis Culin was a mechanic from New Jersey who saw a problem and built a solution with his own hands. He wasn't looking for glory or recognition. He just wanted to stop watching. Good men die for something as simple as an earthen wall covered in bushes. And in doing that, in focusing on the problem rather than seeking credit for the solution, he embodied the best of what ordinary people can achieve when given the chance to try. His story reminds us that the next world-changing innovation might not come from a laboratory or a boardroom. It might come from someone with grease under their fingernails, a notebook full of sketches, and a stubborn refusal to accept that the impossible can't be done. It might come from someone at the bottom of your organizational hierarchy. It might come from someone you didn't expect. It will definitely come from someone you don't recognize yet. The question is whether your organization has the wisdom to listen when that person proposes their unconventional solution, whether you have the courage to say yes, whether you have the willingness to let them try, because the difference between innovation that happens and innovation that never exists might be just that single word, permission. Curtis Culin got that permission, and the world changed because of it. The question for all of us is, who are we not listening to? What solutions are we missing because we've decided in advance that ideas from unexpected sources don't need to be taken seriously? What is our Hedgerow problem? And who is our Curtis Culin, the person we're not giving permission to try?